Hi. You hear me? Okay. So, hi everybody. Today we are going to have a look at how we have integrated React Flow inside of Sirius Web. So the goal of this work was to modernize the diagram support of Sirius Web, but without breaking anything. We had an existing support based on Eclipse Proti, and we wanted to prototype, and if it worked, take advantage of React Flow in order to modernize this part of our application. But for sometimes, we still had to support both technologies. So my name is Stéphane Bégodeau. I'm a software architect on Sirius Web at OBO. I've worked on several projects within the Eclipse Foundation, like EVE or Axeleo, over the past 14 years or so. And today we'll start by a quick overview of Sirius Web, what it does and how it behaves. Then we will have a look at its architecture and specific lifecycle. We'll have a quick overview of React Flow, and then we'll see how we have integrated React Flow inside of Sirius Web, what worked, what did not work, how we could improve the performances, and how we made all this extensible. So Sirius Web, it's an open source platform in order to build domain-specific tools. So you start by defining all the concept of your domain, and then you have the ability to create representations in order to create some specific projections of your data on a specific kind of representation. For example, diagrams, trees, forms, things like that. It provides a modular architecture, so you don't have to reuse Sirius Web as a whole. You can just pick specific parts if you want. And it's also extensible, so if you want to have new features, you can build on top of it. So the first step when you get started with Sirius Web is defining your concept. So here you can see that I've defined a couple of entities with their properties and relation. We'll see a bit more on that in a couple minutes. Here I've defined the description of my diagram, and after that I can start using it to manipulate my data. So if we have a small zoom on the part of my definition, you can see here that I'm specifying that I will create a node for each of my characters, and as a result, I will have a node in my final diagram. So in action, here you can see all of my concept. You have the definition of my diagram with the various nodes that will appear, the various edges, the behavior of the diagram too. So for example, on a node, I have a palette which allows me to create new edges to add a class or to set the race of my character. On the background of the diagram, I have the ability to create new characters, and then when I'm inside of my instance, I can retrieve my tool with the behavior that I've specified a bit earlier. So I can create edges and can create nodes and so on. We can also specify a completely different domain with a completely different kind of tooling. So here it was an example that I made for my son with Pokemon instead. So you can really display anything you like inside of Sirius Web. So all those representations are configured by a specifier. We don't know beforehand how the diagram will behave and how the representation will look. We'll have to interpret what has been defined dynamically. And as a result, the front-end code cannot possibly know what will happen when we will open and interact with a diagram. Nonetheless, our representations are always synchronized with the semantic data. We don't have to be synchronized with everything. The end user can pick a subset of the data to be synchronized with, but representation will always be updated to reflect the state of the data they use. It's also collaborative by nature, so if you change something in one representation, the change will be visible in other representation. And if you have multiple users, if you change something in, if one user changes something, it will be visible for others. So how does it work? We have our backend in Java and the frontend using React components. And for the communication between both parts, we're relying both on HTTP and WebSocket. We have a GraphQL API. All the queries and mutation to retrieve data and change data in the backend are done over HTTP. But to receive real-time update, we are using a GraphQL subscription over WebSocket. So if we look at a very simple example, I have a diagram, a tree on the left and a form on the right, and I want to edit a field inside of my diagram. Here I want to change the name of an attribute. If the end user starts by clicking on this edit button, type some text and hit enter, this is what will happen. The front-end will send an event, an edit label input event, telling the backend that some piece of text has been typed for this specific part of the diagram. It will go to our GraphQL layer with the data fetcher, which will dispatch it to the editing context event processor. You don't have to try to figure out what this name means. It's just the core part of a collaborative layer, which will dispatch events to the relevant part of our code. So here, since we are working on diagram, it will end up on the diagram event processor, and since we try to edit a label, the edit label event handler will handle it. This handler will interpret the specification created by the specifier that I've displayed earlier in the presentation and execute what has been defined. If everything goes right, it will emit a success payload event to the front end. This will tell the front end that the operation has been completed, there's no error. Then it will also, in parallel, emit a change description event that will go back inside of the system. So the change description event will go back to the core of our collaborative part and will be dispatched to all the representations that are currently being used. So here, if I consider that I have only one user displaying a tree, a diagram, and a form, I will have in memory a tree event processor, a diagram event processor, and a form event processor. If there were multiple users with other kind of representations, I would have maybe several instances of a diagram event processor or other kind of representation event processors. Those event processors will receive the change description and decide if they should be refreshed or not. Here, the name of the attribute also appears on the bottom of the tree and in the form. So both representation will be interested in this change description, and they will emit a refreshed event payload. So in parallel of the HTTP request, the front end, which is subscribed to the backend with the WebSocket connection, will receive multiple refreshed event payload to refresh the various parts of the user interface. Those event payload here are received because of a change from my front end, but they could be received because another user had made other kind of changes. In the middle of all this process, we were also relying on the diagram layout engine, which was used by the diagram event processor to compute the layout of a newly created diagram before sending it to the front end. So in our previous architecture, the front end was receiving diagrams properly laid out. We are also tracking the cause and effect of every kind of event that we are inside of our application. So all the events that have been emitted here, the form refreshed event, the diagram tree, the success payload, can all be traced back to the edit label input. We know what has been caused by what kind of event. So this backend layout engine was the source of truth for everything layout related. It was based on Eclipse ELK for the macro layout, so the layout of the nodes in the diagram and the edges. But we had a custom layout algorithm for the micro layout, so for layouting the internal parts of a node, because it's not something that ELK could do for us. We had some bug with this layout algorithm, mainly because of some differences between the backend and the front end. When we ask different web browser on the same computer with the same operating system, the size of a piece of text, different web browser will give you different answers. But when we also ask Java code to compute this information, we had a gap between the result, because not all programming language and platform interpret the size of a pixel in the same fashion. So we started to get interested at React Flow when it started to grow bigger, because when we started Sirius Web, React Flow did not really exist. It was a very small project at the time. But now React Flow is a powerful open source library to build diagrams in React or Svelte. It provides tons of features out of the box. You can customize everything. There's a couple plugins available to have some features freely. And there's an extensive documentation and very large community. You can find tons of examples out there. So it was really interesting for us. So how does it work? So here's the very basic example with React Flow. Here we have a couple of static nodes, so 2 nodes, 1 and 2, one edge from 1 to 2. And then a React component which sets up 2 states, the states of the node and the states of the edges. It gives us in return the list of nodes, edges, and a couple of functions to update the nodes and edges when things are changing. We can use the React Flow React component and just give it back the list of nodes, edges, and a couple of callback when things are modified. And if you do that, you will have on screen your first diagram with 2 nodes and 1 edge. A fairly simple way to get started. Out of the box, you will have node and edge rendering with a nice layout for the edges, which was quite nice to have. You also have features like zooming, panning, the ability to select one or multiple elements. It also provides the ability to create edges between the handles, the small black circle that you can see on the rectangle. And it can be used in one of 2 ways, in a controlled or uncontrolled mode. I'll get back to this later because it's quite important. So with this in mind, we started to integrate Sirius Web and React Flow together. So we wanted to keep having both solutions in parallel in order to be able to evaluate how the new one would behave in comparison to our legacy solution. So we made sure to keep the Sproti support up and running as long as possible to measure the difference in behavior or performance between the 2 solutions. We try at the beginning to reuse as much as possible our data structure and especially the layout data structure, but it proves to be a bit cumbersome with the React Flow part. So our first solution was to just leverage the layout computed by React Flow, and thus if we compared the two diagrams, the Sproti-based one and the React Flow-based one, we would not have the same layout, but we could still compare the internal layout of the nodes and things like that. In the end, we duplicated the layout data structure to have a Sproti-specific layout and React Flow-specific layout because both did not behave exactly the same way. So what was nice with React Flow is that we had React-based code all the way down. Sproti, as a framework, is independent from React and based on a JSX-like solution named SnapDOM. And it can be a great choice for Sproti to be independent from React, to be reused in various contexts, but we are using React code in every single part of our front end. So this independence was not really an advantage for us, but it created some issue and some complexity in our build and prevented us from using React code in some parts of the rendering of the diagram, for example, deep down in the nodes or the edges. So it gave us the opportunity to change the organization of the code and simplify lots of connection that we had to the diagramming framework. It also removed a huge technical bottleneck for us because we had our React code, and in the end, we had to give everything to the entry point of the Sproti support. So we had a very small part of the code that had to be updated every single time we made any improvement on the code of the diagram, creating a lot of conflicts in our Git history. So it's way easier to separate our different components and to have access to things like Apollo GraphQL to perform queries and mutation from the lower parts of the code. It also gave us the ability to remove couplings between parts of our code. And we choose to build this new solution with a lot of small React hooks, each one with a dedicated context when we needed to have some states. So the first thing we started with React Flow was to try to build a custom node and leverage CSS, since we could do everything on the front end, to compute the layout of the node. It turns out, as we imagine, to be very limited for use case. We would need some CSS specification, like CSS Anchor, which are still as a working draft today, which are not supported in every web browser. So we couldn't do what we wanted just with pure CSS. We knew from the start that we would have to rely on JavaScript-based layout algorithm to do what we wanted. One key issue to rely on CSS is that if you have a child node in React Flow, it's not really a child node in the DOM. It's just two DOM elements that are one on top of the other. So you can't just rely on CSS to perform the layout of this part. So we had to choose whether we made the child nodes real child element in the DOM, but we will lose tons of features from React Flow, or build a custom layout algorithm. We still leverage LK, but this time this JavaScript version instead of the Java version, and it works almost the same. We are still very happy with it. So we started experimenting with CSS for the layout of the internal parts of the nodes, and it helps us for the layout of the label. And since it was an issue to compute the size of the label on the back end, now things are way better, because even if we can have a difference between two web browsers, since we are doing it on the front end, we can still fix things when the laid out diagram is sent to the end user. now that the layout algorithm is running inside of the browser. So it changes the workflow of the diagram, because before we were computing the diagram in the backend from the beginning to the end, so the new nodes, the new edges, and the new layout. And now we've changed our strategy. So for that, on the front end, when we receive the diagram refreshed event payload, we also have the cause of the refresh. We can have two cause for the refresh. It can be a layout or the refresh. If the diagram has just been computed, we will go in the refresh part. So in the front end, we will perform the layout and send the layout back to the back end, which will then give the properly laid out diagram to all users. And if we have a cause which is the layout, then we will just set the nodes and edges inside of the React Flow support. So the new algorithm looks a bit like that. So when a change description is sent to the diagram event processor, it will emit a diagram refresh event payload to the front end, saying it's a refresh. The front end will compute the layout and send back the layout information to the back end, which will emit the final diagram refreshed event payload with all the layout information to all the users simultaneously. It's a bit more complicated, but it did not have that much of an impact on performances, and it helped greatly since we could perform the layout algorithm on the front end. So React Flow can be used in two different strategy, control or uncontrolled. We barely tried the controlled approach because it does not give us as much control as we want on the way it behaves. So we quickly switched to the uncontrolled strategy. But even if React Flow tends to encourage you to have the uncontrolled support by default, it comes with tons of default behaviors that are already provided for you. Bit by bit, we switched to custom behavior, but we still delegated a couple of core features like resizing or moving to the default behavior. It gave us the ability to provide additional feature, drag and drop, support for border nodes, things like that. But it turns out to be the source of a couple of bugs. So here you have a small part of the code I showed you before, and this use nodes states on top of the slide is the uncontrolled mode, but it comes with everything set up for you. We change this to stop relying directly on its own nodes change function, and we provided our own with a custom behavior. It allowed us to change the default behavior and then fall back on the original on nodes change function. I'll show you in a minute how we customize this behavior. We then switch to a completely dedicated store, so we stop relying on this use nodes state hook. It gave us a better access to the raw data to perform complex changes. So for example, in React Flow, if we perform a move, it will move the node. But in some cases, we wanted to reset the operation to prevent a move or to have the absolute position to perform some layout computation. So switching to a dedicated store was almost compulsory for us. So with this custom store, we are now in charge of everything. We have our own states for the nodes, for the edges, the function on nodes changes and on edges change are our own, and we can optimize everything inside of this part. It gave us the ability to customize absolutely everything, but this time we are responsible for everything, so we have to ensure we do not create some bugs with what was the default behavior of React Flow. So it gives us the ability to provide a custom resizer. If we try to resize a node, we can say, no, this resize is invalid, return to the original state because it's not big enough to contain everything that is supposed to be inside of a node. It gave us the ability to fine-tune the positioning of the label, to control the layout of the edges, add support for helper lines and things like that. So if we have a look at this, let's go back to Sirius Web. So let's have a look at a couple of examples. So here I have a node selected, and you can see that I have some handles on the corner of my node to resize the node. I can try to resize it to a size which is definitely too small to contain its label. Then we will invalidate this state because we are in charge of this resizing. We have also full control on the layout of the edges. So you can see that we can make sure that we are that we have a nice layout for the edges, but it can go over some nodes in some cases. So we have two modes. One mode which will navigate and make sure not to overlap some nodes. And on the other one, it will draw more direct edges, but they can overlap some of the nodes that are on screen. We have also provided support for helper line, since we can customize everything. So when we are moving the nodes, we can react to that to provide a line to help you align the nodes one with the other. We have also customized the creation of edges. So when we select a node, we have some anchor on all sides of the node, and we can create fake edge between the node and the cursor to select the target of the edge. Here, we are also customizing the behavior to compute the list of possible targets. And you can see here on screen that Jane Doe on the bottom is now barely visible because it's not a valid target. I have two kind of edges that I can create from this node. I have edges to races or classes, and since that's a character, I can't select it. But I could select this one, for example, to create the edge quite easily. We have also provided some features to edit multiple nodes at once. So for example, if I select these three here, I can, let's say, arrange them in a column and then move them over here. But that's here. I could also, for example, change them to this one, arrange them in a row, and I'll make them the same size, like that. We can also control the visibility of the various elements. So, for example, we can, let's say, hide a node and fade another one. We can see the state of our node. So this one is completely hidden, this one is faded, and we can restore them. So we customize tons of very small features of the default behavior of React Flow this way. After that, we worked on performances and how this new solution would compare to the previous one. So the first result was quite good in terms of performances with small diagrams. So that was a good start. And then we start confronting this solution with larger diagram, with much more complex diagram definition. And we detected various kind of performance issues that we could fix quite easily. So the first performance issue was fairly obvious. We had too many event handlers, one per node in some cases. So if you have a diagram with a 1,000 node on screen, it proved to be quite time-consuming. So we made sure that, contrary to some examples in the React Flow documentation, our event handler were at the top of the diagram instead of one event handler per node. That one was easy. Then, as I said before, we split the support of our diagram in tons of small hooks, each with a context. Well, it turns out that updating those contexts could cost us a lot. In fact, we had tons of nodes on screen which were reacting to changes in a context. So when we are starting to draw an edge and we are changing the visibility of the potential target, we would compute this visibility, and it would re-render all the edges, even if we just modified one or two. So we use various memorization features of React to improve this kind of performance issue. But it was really helpful to have access to the full React profiling tooling to detect those kind of issues. React 19 should bring support for the React compiler, which will automatically provide use memo, use callback, and memo features for us. So it should help us in this regard quite a lot. We also leverage the internal APIs of React Flow to subscribe to the state of the diagram. As it's shown in some React Flow example, turns out it can be a real performance killer because this would make some of our nodes or edges directly synchronized with the internal state of the diagram. So anytime something on the diagram changes, all the nodes and all the edges would be updated. So we made this subscription lazy in order to just request what we needed when it was needed. Finally, we made sure to have an extensible solution, and for that, we plugged this React Flow support to our common extension model of the front end. So it comes with an extension registry, not unlike the Eclipse one, with typed extension point, and extensions can contribute either React component, data, or functions, for example. So here are 3 examples that I've selected. So here I have at the top an extension point to contribute new tools to the palette. On the bottom, I have a simplified version of the code. We can just rely on our use components hook to retrieve all the components that are connected to the extension point, and then we just have to display them. One key advantage of this approach is that when you register a new diagram palette tool, for example, you can leverage any React Flow hook in your custom tool. So for example, you want to have access to the state of the diagram, the nodes and edges that are visible or selected inside of the diagram. You can have a look at all that without too much coupling to our code or to React Flow code. And that was a great win for the extensibility of the diagrams. In a similar fashion, you can customize any React Flow property. So this famous onNodeChange function that I mentioned a couple of times, you can replace it and customize it. It's a bit complex, but it gives you access to everything on the diagram if you want to. Finally, you can also configure the communication between the front end and the back end. So if you want to change the queries, mutation, or subscriptions that are sent to the back end, you can do so quite easily too. We have an extension point for that, along with an example. So in the end, it gave us the ability to have a more maintainable solution, especially since we have React code all the way down of our code base. It also improved performances. We could have improved performances on the previous solution, but since we now can use React patterns and profiling tools, it's very easy for us to do so. And we now have an extensible solution with a very nice and consistent API for all of the front end, and that was a great win. Thank you for attending this presentation. If you have any question, don't hesitate. And I think we are a bit late, so if you don't have any question, you can just find me at the OBO booth, or I will present another part of our work on Sirius Web. We made this platform modular and extensible later today. Thank you.